In this video, we're going to look at a few more infinite series, and we're going to be evaluating these series for whether they converge or whether they diverge. So question A, summation n goes from 1 to infinity e to the 2n divided by n squared. Part B, summation n goes from 1 to infinity arctangent of n divided by n plus 1. Part C, summation n goes from 1 to infinity cosine of n pi times n divided by 2n plus 1. Let's look at part A. So let's take the limit as n approaches infinity of an. This is equal to limit as n goes to infinity of the nth term, which is e to the 2n divided by n squared. Now, if we plug in a very large number when n approaches infinity, you can clearly see that we get infinity over infinity pattern, because the exponential function e to the 2x approaches infinity as x goes to infinity, so e to the 2n approaches infinity as n goes to infinity. And similarly, for the denominator, the quadratic function x squared approaches infinity when x approaches infinity, so n squared approaches infinity as n goes to infinity. So we have infinity over infinity pattern. We're going to apply L'Hopital's rule. L'Hopital's rule. All right, so we have limit as n goes to infinity e to the 2n divided by n squared. Apply L'Hopital's rule. We get limit n goes to infinity, differentiate the numerator, we get e to the 2n, apply the chain rule, times the derivative of the exponent, we get 2, divided by, differentiate the denominator, derivative of n squared will be 2n. Now we still have infinity over infinity, so we have to apply one more application of L'Hopital's rule. So differentiate the top and take the limit. Limit n goes to infinity, differentiate e to the 2n, we get e to the 2n, times the derivative of the exponent, which is 2, divided by, differentiate the bottom, derivative of n is just going to be 1. Now take the limit, and the limit is infinity. This limit is not equal to 0, and since the limit of the nth term, the limit as n goes to infinity of an, does not equal to 0, this series diverges. This series diverges by the divergence test. Recall the divergence test, take the limit of the nth term. If the limit is not 0 or does not exist, then basically we say the whole series diverges by the divergence test. Now part B, we have limit n goes to infinity arctangent tan minus 1 of n divided by n plus 1. Let's bring the limit inside the brackets. So we have tan minus 1 of the limit as n goes to infinity, n divided by n plus 1, divide by the highest power in the denominator, and take the limit, we get tan minus 1 of 1. What is arctangent of 1? This is saying what is the angle whose tangent is 1? Of course, the answer is pi over 4, because tangent of pi over 4 is equal to 1. In any case, pi over 4 does not equal to 0. That means the limit of the nth term, limit n approaches infinity, of an is equal to pi over 4, does not equal to 0. This series diverges. This series diverges by the divergence test. All right, let's look at another example. Let's investigate an is equal to cosine n pi times n divided by 2n plus 1. So let's look at cosine n pi. So we have cosine of n pi. This is equal to 1 when n is even. For example, cosine of 2 pi, cos of 2 pi is equal to cosine of 4 pi is equal to cosine of 6 pi, and so on. Any even multiple of pi will give us 1. And is -1. Cosine of n pi is equal to -1 when n is odd. For example, cosine of 1 pi, cosine of pi, or cosine of 3 pi, or any odd multiple of pi will give us 1. Sorry, it gives us -1. So that gives us -1. All right, so in general, we can see that cosine of n pi can be rewritten as -1 to the power of n. Because when n is even, you get -1 squared, for example, is equal to 1. And when n is odd, we get -1 cubed, which gives us -1. So now we can rewrite the general term of this infinite series, an is equal to cosine of n pi times n divided by 2n plus 1. We can rewrite this as -1 to the power of n times n divided by 2n plus 1. So we have an is equal to -1 to the n. We have rewritten it in an equivalent form. This is exactly the same as before, except we just rewrote cosine n pi as -1 to the n, because cos of n pi is equal to -1 to the n. Now, when n is odd, this is going to be -1 to the n will be -1, so we just get -n divided by 2n plus 1 when n is odd. And an is equal to -1 to the n times n divided by 2n plus 1 is equal to n divided by 2n plus 1 when n is even, because -1 to the n is equal to plus 1. So what we have is an is equal to -1 to the n times n divided by 2n plus 1 is equal to -n divided by 2n plus 1 when n is odd, and n divided by 2n plus 1 when n is even. So let's take the limit as n goes to infinity of an. We get limit as n goes to infinity of -n divided by 2n plus 1, dividing by the highest power in the denominator and taking a limit, we get -1/2. The limit of the nth term an is equal to -1/2 when n is an odd integer. Now let's take the limit as n goes to infinity of an when n is an even integer. This is equal to limit n goes to infinity, n divided by 2n plus 1. This gives us 1/2, dividing by the highest power and taking a limit. So we get 1/2 as a limit of the nth term when n is even. So we can see that the limit as n goes to infinity of an oscillates between -1 and 1, depending on n being an odd number, odd integer, or n being an even integer. So therefore, the limit as n goes to infinity of an is equal to limit n goes to infinity of cosine n pi times n divided by 2n plus 1 does not exist. Does not exist. This series diverges. This series diverges by the divergence test. And by the infinite series, we mean summation n equals 1 to infinity, n equals 1 to infinity, cosine n pi times n divided by 2n plus 1 this infinite series diverges by the divergence test. So this is a very good test to apply in the beginning, because if the limit is not 0, or if the limit of the nth term does not exist, then automatically you can rule out convergence and say this infinite series diverges for sure, and you don't have to do anything after that. If the limit was 0, then you have to apply another convergence test that we'll be looking at in the coming videos. All right, thanks.